Hello to all of you to our Infoshare today. We are conducting this Infoshare as part of the work package 6, network development in the GÉANT 5.2 project. And we have picked this topic of operational aspects for quantum communication networks because we see more and more NRENs implementing QKD networks, and so we thought this would be quite an interesting topic to focus on. We have 3 presentations. The first one will be focusing on cross-border collaboration and operational aspects of that. It is presented by Alexios, Aivaliotis, and Konstantinos Tsimvrakidis from GRNET and NTUA in Greece. Then the second presentation will have monitoring tools as a main topic and also the integration with fiber sensing. This presentation will be given by Piotr Rydlichowski from PCSS, formerly known as PSNC. And the third presentation will be talking about enabling synchronous quantum networks using timing via synchronous Ethernet and PTP. And this will be presented by Marc Jofre from the Department of Network Engineering at the Universitat Politècnica de Catalunya, BarcelonaTech.
Good evening, everyone. My name is Aivaliotis. I work at GRNET, the Greek National Infrastructure for Research and Technology. Today, with my colleague Dr. Konstantinos Tsimvrakidis from the National Kapodistrian University of Athens, or the University of Athens simply, will present to you about the HellasQCI project and the demonstration that took place during the QCI days in Athens 2025, which was a cross-border collaboration between Greece, Austria, and Spain. So, just a very, very quick overview of the presentation. So, first I will speak a bit about the HellasQCI project and the QCI days event in 2025. And then Konstantinos will take over to discuss a bit more about the demonstration that took place there. So first, let me begin by saying that Greece has been very actively engaged in EuroQCI since 2019 when we signed the declaration, the EuroQCI declaration. Quantum communications are embedded in our national digital transformation strategies, the first one from 2020 to 2025 and has been extended until 2028. And Greece is also preparing a national quantum strategy that is aligned with the EU quantum strategy, the recently published EU quantum strategy, while in parallel we've participated in other EuroQCI calls such as the CEF call and the upcoming IRIS² call. The HellasQCI project, or the national QKD network that we've been building is a project funded by the EuroQCI, and it aims at building our national QKD network, as I said. So it includes 3 metropolitan test sites in Athens, Thessaloniki, and Heraklion in Crete. And these networks connect to 3 observatories, which are the optical ground stations, the ORGSs at Helmos, Skinakas, and Holomondas. In total, we're deploying 27 QKD nodes across government, education, and industry. And this setup allows us to test real-world use cases, build skills, and train users. Next slide, please. So the HellasQCI architecture, as it has been set up, it's designed in 3 layers. The first layer includes the QKD layer, which supports relayed direct variable QKD, switch QKD, and also partial mesh deployment in flexible topologies. The middle layer, which is the key management system, manages key distribution and interfaces with applications which are fully aligned with ETSI standards. And finally, we have the application layer, which supports encryptions from layer 1 to 3 and remains compatible with classical encryption methods. A proof of concept was designed to validate this architecture in a real field deployed testbed. So this testbed was 45-kilometer wide network in 3-node full ring configuration, which connected GRNET to NTUA. And this architecture was validated and showed basically that hybrid quantum classical key management is both possible and efficient. So next slide, please. This proof of concept has also been expanded during our project, during our HellasQCI project, and has been sort of upgraded into what we now call the Athens Quantum Network. So this network spans 120 kilometers with 5 physical links between GRNET, the National Technical University of Athens, the University of Athens, and the National Center for Scientific Research Demokritos. It supports 8 nodes and is actually quite crucial for testing QKD devices and validating their performance and use cases. So next slide, please. Another very, very important aspect of HellasQCI is, except from the actual building of the quantum network, is training. So we aim to train the new generations of quantum experts and engineers. So we address the needs of academic and research staff, experts in digital security, as well as end users from the public and private sector. We've held a variety of smaller scale training events, but also we've organized already 2 very large training events, a workshop on QKD systems and cybersecurity with QKD and PQC, which took place in Athens in September 2023, and also a workshop on EuroQCI deployments and cooperation and cybersecurity with QKD and PQC, which took place in Crete, in Heraklion, in September 2024. These 2 large-scale events and the smaller scale ones until now total to more than 50 lessons performed and 6 labs, and have attracted a total of 800 attendees, both online and physical. And we've also organized a visit to the Skinakas optical ground station when we did the event in Crete. And the final event is going to be organized in Thessaloniki now in November 2025. It will be a workshop on space-based QKD, and will include a visit to the Holomondas OGS in the northern part of Greece. Okay, next slide, please. And the third pillar, which will now, when we're coming to the QCI days, the third pillar of HellasQCI is the engagement with the EuroQCI community. We participate in meetings of Petrus working groups and regular meetings of the Nostradamus projects. We contribute and participate in conferences and workshops organized by the EuroQCI community. And we have also established the HellasQCI community, which comprises of national stakeholders that benefit and support the network that is being built. We try to raise awareness and ensure better participation in the EuroQCI community and leverage new end users for the expansion of the network. Until now, we've attracted more than 28 registrations from the governmental, educational, and industry sectors, and are registered into the HellasQCI community. And also, as I mentioned before, Greece participated in the EuroQCI CEF call with 2 successful proposals. And all this culminated in the organization of the QCI Days 2025 in Greece event, which was held here in Athens in April. During the event, we attracted more than 300 physical attendees and 300 unique daily viewers via our online platform. and more than 30 countries were represented, as well as 25 national QCI projects and 6 industrial QCI projects. We had more than 90 speakers and two keynote speakers, Professor Arthur Eckert from the University of Oxford and Dr. Eleni Diamanti from the CNRS. And we also had 20 technology providers as exhibitors. We had 6 panels and live Q&A sessions. And this entire event was very widely covered in 81 articles, both online and the press, and also in the Greek public television. The event also attracted very high-level engagement. So we had the Minister of Digital Governance, Mr. Papastergiou, who participated and actually gave a speech in the event, and the Secretary General of Telecommunications and Post, who is responsible for the EuroQCI in Greece. So that's all from me, I think. Of course, you're welcome to post questions in the chat, and you're more than welcome to register to our upcoming HellasQCI training event in November in Thessaloniki, and I will hand over to Konstantinos Tsimvrakidis to tell you a bit more about the demo that was held there in QCI days. Thank you.
Thank you, Alexis. I'll pick it up from here. As Alexis said, the event was co-organized by 3 QCI teams: the Greek one, the HellasQCI team, the QCI-Cat from Austria, and the EuroQCI Spain. So, organizing the event, we also tried to demonstrate a quantum network that goes beyond the bounds of a single domain. So we built a cross-border, if you like, inter-domain quantum network, having, as you can see here, 3 racks, each one representing a country or a domain. So the Austria one had 3 QKD nodes, as well as the Spanish domain, and Greece had a total 5 QKD nodes in the rack. So this is a high-level schematic of what we accomplished there. It has the rack nodes, the ones you saw in the picture before. That's what we had to demonstrate in the venue, the QCI Days event. And we also had a fiber pair that would extend the connectivity for the Greek domain of the venue. So we had an optical fiber pair that would left the venue and went and connected to the Athens quantum network, the field deployed network. As you can see, that's the map on the left-hand side, where you can see on the left down is the Vinidis Foundation. That's where the event took place and how it's connected to the rest of the Athens quantum network. And that's as Alexis said, is a educational network as it stands right now. But the next steps of the HellasQCI, it's going to be expanded with industrial and governmental nodes and be a really advanced and complex network. But at this point, we have only educational nodes just to test and carry out the use cases. And that's what we connected to the venue. So as an overview, what we had there was a multi-node quantum network. We had a total of 11 rack nodes on venue and the 4 physical nodes of the Athens quantum network. We built that with different QKD vendor systems. So we had ID Quantic, ThinQuantum, KeyQuant, and QTI. From HellasQCI, we used all our own QKD systems. So we had a total of 9 ID Quantic pairs and 4 of the ThinQuantum pairs. These are deployed across our Greek domain and also the Spanish domain. And for the Austrian one, they had the KeyQuants and the QTIs. We also had multi-layered key management That means that we used multiple KMSs, either integrated into the QKD systems themselves, or we had the external ones. And I'm gonna discuss that in the next slides. As I said, it was a multi-domain network. That means that each of the racks represented a different domain, and we achieved a connection between these three domains. There were multi-service network. That means we had demonstrations and applications across different layers of the OSI model, and that's the OTNSec, MACsec, IPsec, and also directly in the application layer. And as I've already mentioned, they had also a click domain field deployed segment that extended to the Athens quantum network. So, so going step by step, first of all, the QKD layer, that's the physical layer where actually the QKD keys are generated. So we have different systems. We have discrete variable QKD, DVQKD, based on the phase and typing encoding, such as the ID quantique LAVISXG and the QTIs. And also we have the DVQKD with polarization-based encoding. That's from ThinkQuantum, and also CPQKD from QQuant. So what we actually had there was we built a total of 15 nodes with 13 QKD pairs, and we deployed them in arbitrary topologies. As you can see, we had from simple P2P and relays all the way to a star topology that would either extend to a second star, and that would also have as an extension different P2Ps or relays or even a ring, as you can see down in the bottom. Next, for the KMS layer, that's the key management system. It's where we actually store the QKD generated keys and handles the key material, decides how to actually use that and where to forward it. So as I mentioned, we had different KMSs. So we had the proprietary QKD vendor KMSs. That's the embedded KMSs that are with that come with the QKD systems. The ID quantic one, the ThinkQuantum, the QQuant, and the QTI ones. And these KMSs they comply to the ETSI 14 standard, and that means they bring the interface to receive keys and the push keys to other KMSs that also comply to the ETSI 14 interface. We, in the Greek domain, we also used a third-party KMS from EvolutionQ. That's the base jump KMS. And we solely use that to support our layer 1 network service. That's the network with the Nokia, the blue labels forming a ring from the venue and the Athens quantum network. And also we used the KMS systems from QNET. QNET is the spin-off of the Universitat Politècnica de Madrid from the EuroQCI Spain. So they have built this KMS that has an extension and can actually perform the ETSI 20 interface. That's an interface that's not yet standardized, but it's on its way. And that interface allows different domains to connect to each other. So what happens is at the edge of your network, at the gateway node, this node actually receives a request for a key from the other network and just forwards it without knowing any other information on the other's network. So we used this CoolNet KMS on top of ours, and also for the Spanish domain. And the Austrian domain used their own AIT KMS that used actually a script and extension of the CoolNet so they could communicate over the DTSI-20. And that's how we were able to support the inter-domain connectivity across all three domains. Next, on the top layer, the application layer. So we actually had different encryption layers. We had the layer 1, the OTN-SEC, using the Nokia systems. These were 3 encryptors, as you can see in the Greek node 5 and the GRNET and NTUA node. They form a closed ring where they can transfer data up to 500 gigabit per second per line. And what's not shown here is that we also had a Nokia orchestrator, that's the Nokia SMS security management system, that it could actually regulate and orchestrate the keys, and they could provision the key requirements from the encryptors. And it could also have this feature that it could generate its own classical keys in case of there's something wrong with your QKD network. So it could use this hybrid scheme and support your network so there's no downtime at all. So for layer 2, we had 2 different vendors. We had layer 2 encryptors from Juniper and Arista. And for the layer 3 encryption on the IPsec, we had FortiGate firewalls where we could establish VPN tunnels. And we actually demonstrated that in 2 different ways. We had through a cable that would transfer up to 100G per tunnel, or we could also establish this QKD encrypted VPN over the internet. And also in the application layer, we had various demonstrations from Qubitech, from Thalys and WireGuard, and we also had this video conference from using the GG open source software. So what we demonstrated for the first time through this cross-domain network is that we established a 4-node video conference. That was a video conference that was crossing multiple nodes while having multiple other consumers in between. So its network was independent and could establish this conference with the other domains. We do that using our FortiGate firewalls, as you can see for the on-venue node, but it could also extend using a MACsec through the Aristas to the NTUA, where we could actually it's not NTUA, it's GRNET, when we could have the 4th node. And we did that while having all the other mini demos and inter-domain demonstrations and services running for all the 3 days. And that's actually the closest you can get to real-world deployments. We had this cross-border video conference that would work perfectly while there are multiple other services running in the background. So we also had these inter-domain mini demos. I'm not gonna go deep into the Spain and the Austria domains. They had these these mini demonstrations where they could show the IPsec tunnels for health applications, and for Austria the chat and video with QKD and PQC through the Thalys equipment and WireGuard using the HSMs. But for on our domain, for our Greek interdomain demonstrations, we could showcase a software that we developed within the HellasQCI. That's a monitoring tool that SpaceLabs developed based on the Elastic in collaboration with the NTUA and the GRNET. And that offered a centralized collection of the QKD network data that we later used for indexing, visualization, and further analysis. What we could have there was in real time, we could get the QKD metrics such as the SKR, the QBER, and key buffers, and have a live feedback on that. That's what we showed back then. Right now, we're working on expanding that. That means that we can get further input from the QKD network, and we can actually have some alerts and event detection. And maybe in the future, we can also incorporate some machine learning algorithms and make it actually smart. Next, we have this video conference, as you can see here, marked in the schematic. That's a QKD enhanced software app that was developed by Qubitech. That's a partner in the HellasQCI. So they could actually demonstrate a quantum encrypted video conference software that would get keys directly from the KMSs and establish a high quality end-to-end encryption video communication between the two parties. Next, we have these pink boxes, as you can see here. These are actually path authenticators. So we actually used these systems that were developed by Qubitech. They were based on a theoretical model that was developed by Forth. And Qubitech, in collaboration with the NTUA, they managed to integrate these path authenticators and make them work with thin quantum systems. So what they did was use these path challenges and achieve the initial authentication between the QKD pairs by passing the standard preset key method of the system, and actually strengthen the initial authentication of the system. And while we used path authentication, right now we can actually use as well PQC algorithms to do the same job and strengthen the authentication. Finally, as also we have this FSO link, as you can see in the bottom. That's an FSO link that is intercepting a QKD link between NTUA and NKUA. So we had this fiber link, 100-meter fiber link, FSO link established on the rooftop, on two of the rooftops of the NTUA campus buildings. And we had this wireless fiber scheme where we could transfer the quantum information and establish the quantum channel between the Alice and Bob. And with that, I conclude what we demonstrated in the high level and all the mini ones in our the QCI days in Athens this year. And thank you very much. If you have any questions, we are pleased to answer them.
So thank you again for joining the event. So I will try to focus today on a little bit, not maybe specifically on a QKD systems and devices, but more on the operational side. So talk a little bit about the need for the monitoring the network and the maintenance activities connected with these type of activities and running this kind of the services and channels within your network, and how potentially you can connect this with sensing application, because to be honest, the quantum channel, regardless of being used to share and transmit the data, can be used simply as a sensing channel for some untypical applications and scenarios. So I will start just very short few words about the network that we have. So PCSS is the coordinator of the Polish QCI project, which is Pioneer Q. So it's a complementary network to our existing NREN Pioneer network. At the moment, this network is connecting all the 5 HPC centers in Poland, so between Poznań, Gdańsk, Warsaw, Wrocław, and Kraków. So we have at the moment 1,770 kilometers of the long distance QKD links. It's about 60 devices, QKD devices at the moment within the setup of trusted nodes. So it's a mix of the topologies between the trusted node and the star topology. And also this backbone network is connected to the local small QKD setups with few QKD systems that are running and acting as an access level to the QCI network. So in this sense, you can say that it's a multi-layer approach. So on one side, you have an access QKD systems, which are governed by the separate QKD system. And then you have a backbone QKD network with its own KMS system. And then on top of that, you can have intercity QKD network that can be managed by another KMS system. So it's consistent with what our colleagues from HellasQCI showed at the demo. So you have 3 different KMS system for each country, but to be honest, you can have those KMS systems independent for another levels also of your network. And in the end, you can interconnect them with ETSI. In the case of the demo that colleagues ran in Athens, it was ETSI 020 that interconnected the KMS. So it's a nice, really nice presentation and setup what you can achieve with this KMS multi-level approach. So now leaving a little bit the QKD technology itself and moving to the monitoring. So in our case, I will share some few thoughts and activities that we did, what we implemented. So the QKD network and the KMS system that we have, it's constantly monitored by our NOC for our whole NREN network. It's also they monitor the full QKD system capabilities. On one side, it's a SNMP monitoring, but on the other side, we have some independent monitoring of the devices, which I will speak a little bit later. So that we've introduced a ticketing system, usually in each network that you have. So each problem with the QKD system, either with the performance, with the variation, with the temperatures, with the operational conditions, it's put in the ticket, and it's handled by our network administrator. And regardless of that, we have daily verification of all the QKD segment and the performance of the quantum channel. So just to additionally verify any deviation and changes within the system that you might observe. So it's all for QKD hardware and also for the KMS and supporting software for KMS. We'd also monitor the QCI system during the maintenance work that we have, as you can expect. you have the fiber cuts, maintenance work. So then you need to stop the QKD transmission. Then you can of course, you can run it in automatic mode. So once the connection is brought up, you can automatically set up the quantum channel. But I think, in my view, I think it's not always the best case, because usually when you have the fiber cut at the end of the repair, the maintenance works, you need to do the OTDR, the measurement, and then if you do not have the quantum channel disconnected on both sides, it's not that beneficial for the QPD equipment. So it's you can do it, but it's safer to do the QKD channel verification using OTDR externally. Now, of course, the QKD systems, they can also estimate based on the classical signals that are being transmitted, not the quantum channel, the attenuation of the link. But after the maintenance work, the procedure is that you do the OTDMR measurement of the fiber and the dark fiber that you use for the quantum channels. So in our case, all the QKD systems are running on the dedicated dark fiber. And what also what we've introduced actually a few years already, I think 5 years ago, is that we do not allow to introduce any new splices and new connection to our fiber segments. So in case of the major fiber cut, we exchange the whole segment, maybe not the whole fiber segment, but the fabrication length. Usually it's either done that you replace the slack, or you just pull enough of the fiber slack from the next reserve of the fiber. So in special cases where the conditions justify, of course, it may be not possible to do, but usually so far what we do is that we do not allow to add a new splices, so that way you can control the performance and the quality of the fiber that you have. And also, I forgot to mention that apart from the dark fibers that we use, we also use the polarization maintaining, polarization compensating fibers. It's also untypical. You usually run the fibers on a standard G652, but we run our QKD systems on G655 fibers. What we additionally introduced, that is apart from the QKD systems itself, is that we have in each our trusted node and node external additional temperature monitoring. Why we do it? Because we also would like to see the variations of the temperatures within the nodes and for the devices, so the cooling performance that we have. So apart of that, we have redundant virtual machines that run the key management instances. It's on one side, it's used for redundancy. So in case you have problems, you can switch the KMS. But also it's it's introduced for testing and simulation purposes. So you can run a parallel mirror a network on your separate KMS, and then you can experiment with the changes and do the testing before to deploy the changes in the real network. So it's the same approach that you have in the operational network, that you first need to test any changes before you deploy them. And then we have a tool for logging, for analyzing the logs. So the QKD systems at the moment, they also can produce a lot of interesting logs and the data that you can analyze later. So it's quite also interesting traffic and patterns. So we also do log this kind of data. And now going back a little bit to the QKD system itself. So As you know, the QKD system and the quantum channel it's sensitive to the fiber strain. So the actual quantum bit error rate that you observe can be introduced, and usually is introduced by the fiber strain, which is correlated to the any physical changes that you do to the fiber. And you can correlate also those changes with the fiber measuring system that are also sensitive to the fiber strain. It's not easy to connect and to correlate, but it's an interesting option that we also are trying to pursue and test. And just a short screen of our NOC that we, this is the commercial KMS that we have from IDQ that is also being monitored and tested. A part of that, we have the ticketing and monitoring system, which is based on our IBM infrastructure that it's collecting all the problems, all the tickets, and the problems on the devices. And also externally using Grafana interface, we do the analysis of monitoring of the performance. In this case, the key rate, the visibility, the quantum bit error rate, but you can do it for every parameter that you have for your QKD systems. And now, the temperature stability. So this is what we introduced, not for all the nodes, but you can see that if you have variations in your temperature in the node, especially close to the QKD system, you can observe the variation in the in the secret key rate. You can see that it's consistent with the changes of the temperature. And the problem is not the change of the temperature, but the speed of the change of the temperature. So if you have a rapid 1 minute, below 1 minute change in the temperature, you can see that it's around 2 degrees. Then the QKD systems, they need to adapt, and if you do it quite fast, it can be problematic for the devices. So that's why it may be when you in the situation where you notice this kind of the variation of the key rate, you can introduce the monitoring and the tracking of those temperature changes. And it is always, and what we've observed also is you need to take a little bit of trade-off. So either you can have a stable temperature, but it's a little bit higher than it might be, or you can go for the lower temperature, but then you can have a little bit higher deviations of this temperature. So it's not always the case, but usually with the classical implementation of the networking nodes, it's usually either stability of the stable temperature levels. And now to the final part with the acoustic sensing. So as you probably may already be aware of, that the distributed acoustic system is an interesting device that can monitor activities which are happening around the fiber. And it's using the strain, the measurement of the strain of the fiber to reflect the changes of the acoustic events that are coming to the, that are being transmitted to the fiber. So the acoustic waves, they produce the strain of the fiber, and you can monitor this. So it might be interesting to change and correlate those events also with the variations of the performance of the quantum channel, especially the quantum bit error rate within your system. What is interesting is that for the QKD channel, you can only see the performance end to end. You cannot determine where you have a potential problem on your quantum channel, on in which exactly location. It's not possible at the moment. You can only do it end to end. And when you have additional measuring system along the fiber, such as DAS or other fiber monitoring tools, you can potentially try to track the exact location where you can have this system, when you can have potential problems. So you can treat the quantum channel, regardless of the transmission, as an additional kind of a sensor. And so, as I mentioned, in our network, the quantum channel, it's running on a dedicated dark fibers, and a few months ago, on one of the QKD segments that we are running in our backbone network, around 90 kilometers, we also, in the same cable, on the neighboring fibers, we deployed the acoustic sensing monitoring. And what is interesting is that this fiber route is running along the railway tracks. And even though on top of it, also the few first kilometers of the cable, it's exposed. It's lying on the ground near the railway tracks because it's during the maintenance and reconstruction. So it is a very good opportunity to not only monitor the influence on the QKD quantum channel, but also on the DAS and DAS system. So within this one segment, you can observe different things connected with the quantum channel and the DAS measurement. And just complementing the measuring activities, so you can also correlate those events with reference time and frequency, but I will not speak a little bit more about that because it will be our colleagues during the next presentation will elaborate about the synchronization and the time and frequency that you have in the quantum channel. But we already did in the Open QKD projects together with our colleagues from CESNET some tests with co-propagation and some initial analysis. And also with two in TNC22, apologies, we already had some initial presentation, what we did together with our colleagues from ADVA, and now it's ATTRAN, as they are implementing machine learning solutions to their WDM system monitoring. We added some additional elements that will allow also for the QKD network monitoring analysis of the traffic from the quantum channel. Some initial analysis, especially for the on the performance of the fiber. And now going a little bit for the DAS. So as you can see the movement of the cars and the trains, the speed of the trains in the different directions along the tracks. But what is interesting, maybe I will switch to this slide. You can also observe a higher activity near the railway station. So you can see it's a few kilometers, which is closer to the end segment of the fiber. There you can see that it's more activity along the railway station, and then along the fiber itself, you can see a heavy train traffic. Especially here, you can see these are the different types of the trains. So passenger train, and when you have a really good signature, it's a heavy transport train. You can also see, depending on the speed, because the transport trains, they usually travel with a lower speed and events. And you can also observe when the trains stop because the track is not clear for them. But now we are trying to analyze and correlate with the different events on the WDM and the QKD systems that we have at the moment. But the trouble, as you can see, there are a lot of events, so you also need to introduce a little bit monitoring to to manage this kind of the traffic. Yeah, so thank you. So to catch up a little with our timeline for the presentation today, this would be all. So I would be happy to take some questions and either now or during the Q&A session.
This talk is centered on quantum networks, by meaning that multiple nodes are interconnected, eventually to in the future relay entangled qubits through the network. So this is a little bit the context of this talk. Rather than QKD specifically. So for that, for transferring entangled photon source qubits or qubits, time synchronization is important. You all know, especially because currently we still don't have, let's say, reliable quantum memories. Okay, once we have some commercial quantum memories or high-performing quantum memories, maybe all these time synchronization requirements will be lowered or can be lowered, right? So mainly the idea of synchronization has already been done in telecom networks. You all know how your computer synchronizes to the global time with the network time protocol. And also you know that there are more precise protocols that achieve microseconds or nanosecond accuracy in telecom networks, right? But for quantum networks, because we have to either timestamp detections or we have to verify entanglement, so we have to make the two qubits interfere. So this means that they come together in time and in place. Then the requirement for synchronization is much higher, eventually in the picosecond, tens of picosecond range, right? For this, well, there are these techniques to synchronize networks, which, from our point of view, reduce the usage of bandwidth, and they are scalable to many nodes, eventually hundreds of nodes, all being synchronized. So this is the context of this presentation. Also, it's focused on discrete variables rather than continuous variables for quantum networks. So, well, some numbers, some precision requirements for time tagging. Typically, you are okay with hundreds of picoseconds, and this is achievable by time tagging units and also by detectors, single photon detectors, so no problem. For entanglement distribution, so that you have to perform Bell state measurements, so you have to make the qubits interfere, then maybe we need sub 100 picosecond accuracy, and eventually for quantum repeaters or without memories, we would need less than 10 picoseconds, okay? And so how can we achieve this today? Well, the GPS typically provides a few nanoseconds precision. Of course, you have to have vision to satellites. Maybe it's not the most convenient for fiber deployed networks. Then you can use fiber-based synchronization signals. You can achieve less than 100 picoseconds. But of course, you consume a lot of bandwidth. You consume continuously the channel for transmitting the synchronization rather than sending qubits or data. Of course, then there are also optical references, which you can achieve below 10 picoseconds accuracy over large distances, of course, because they are independent. But, well, you need a optical reference in each node you want to synchronize, and still you will need to at least synchronize the offset between the different nodes, right? And finally, if you have some synchronization, you can think of running some quantum synchronization protocols. But for doing this, you already need some previous synchronization. So it's let's say a closed loop that you have to solve first the regular synchronization. So for that, well, there are some protocols, you might know them, which are the combination of synchronous Ethernet, which is widely deployed in telecom networks for specific use cases, and the precision time protocol. So the combination of these two allows you to achieve picoseconds or tens of picoseconds accuracy in the synchronization. I want to be clear here. Some of you might know these synchronization techniques by White Rabbit, right? White Rabbit developed at CERN. It's a combination of synchronous Ethernet and precision time protocol together with some phase alignment. But the concept behind is these two systems. Of course, here the idea also is that synchronous Ethernet is a physical layer protocol. Basically, you send while transmitting data, you send your carrier, your frequency, your clock. And so at the other side, you have a PLL, and this PLL locks into this signal, right? So you have a physical layer part, which is the synchronous Ethernet. And then you have a TCP/IP step where messages are exchanged between the master and the node. We will talk about this later. And inside these messages, you have timestamps, and by doing some processing, you compute the offset and you synchronize, right? And as you can see already here, there are different planes. A physical plane, but also a control plane where messages are exchanged, right? And this is nice because what we will try to show here today is that we can manage to achieve picosecond synchronization in the physical plane and some microsecond synchronization accuracy in the control plane. Yes, so this is a little bit the idea. So here are the planes as we imagine them. So on the left side, it's the common telecom planes where you have a time phase plane where these PTP messages are exchanged. And so in your operating system, on your node, the operating system running, it can achieve microsecond synchronization. And then on the physical plane, you have this frequency distribution, this synchronous Ethernet. And by combining both of them, you can have this nice synchronization. Here, now we have to think about adding what we call the quantum plane or the real-time quantum plane, because in the quantum plane, you have to process information in real time. And so by having in mind these planes, again, we can achieve picosecond accuracy in the real-time quantum plane, important for time tagging, for interference, etc. And in the control plane, which mainly is running on your operating system, your Linux or your Windows system, we achieve microsecond synchronization. Just some basics. A synchronization, at the end of the day, a basic scheme is that you have an offset, delta t, and a relative frequency difference, delta u, and these are your unknowns, and by running these protocols, it's what you can derive, and so you can time synchronize the different nodes. I will not extend myself, but this is the scheme of the precision time protocol, where there is a master and then there is a slave, and the slave keeps asking the master for delay requests. So what's the time to transfer and receive back the message? By running this, it's possible to achieve microsecond or 100 nanosecond accuracy in the control plane. So by this we mean in our operating system, the one that takes let's say that performs logics. So for instance, you can think of distributing or allocating different nodes to transmit at a specific time slots. And so this is the control plane that needs to do it, right? Not the quantum plane. It's the control plane that sees that it's the time for transmission, okay? While on the physical plane, this synchronous Ethernet, together with the precision time protocol, phase synchronization can be achieved. So phase synchronization is more than frequency synchronization. Frequency synchronization means that both clocks clock at the same frequency, and phase synchronization means that they clock at the same frequency and with the same phase, so they start at the same time, okay? So this is the combination of synchronous Ethernet and PTP, also known as White Rabbit. And here we did a test rig with 3 nodes. Here are the pictures. The first iteration didn't have synchronous Ethernet, while the second iteration had synchronous Ethernet plus PTP and some FPGAs. And to extend myself, here we can see how they synchronize in the physical plane. Here you will see 2 signals that are unlocked, and suddenly they lock in, and by taking the histogram of the jitter, we can see that we achieved around 100 picosecond synchronization. Also, with more than 2 nodes or 3 nodes, this lock-in also occurs, and now the 3 nodes are phase synchronized to 100 picoseconds, right? So this is the beauty, we believe, of these kind of synchronization systems for synchronizing multiple nodes, to then be able to perform, for instance, time division multiple access, and bell tests, and qubit time tagging, etc. So we think that there are many conveniences to using this sort of systems. Of course, I don't want to say it's a perfect thing, because this synchronization happens typically on fibers where the qubits are not transmitted. So what we are talking about here is synchronizing the nodes on time. Then there is some work to be done to synchronize the qubits. So you have to measure some qubits and do some either correlations, or here we propose to use some put a pattern on the frequency of qubit transmission, in order to then cross-correlate at the receiver to see time offsets and relative frequency differences at the qubit level. So again, time synchronization with these white rabbit systems is for synchronizing the nodes. Then you have to run some algorithms and measurements to synchronize actually your qubits. Okay, I want to be clear with that. And to end up with this presentation, just to mention that, of course, there are other limitations, typically distance limitations. So this white rabbit protocol might work correctly for hundreds of kilometers, but when you go to the very far end, then issues come up. So we'll keep working on this through our projects and try to increase this synchronization distance to the maximum, eventually 1,000 kilometers, who knows, because we believe in this kind of synchronization for many nodes for networks. And that's it. Thanks a lot. And if there's any question,